Good evening. My name's Amy, and I'm a librarian here at the Ann Arbor District Library. Thanks for coming out for the show tonight. I just want to give a quick announcement before I introduce Jason. If you like what you see tonight, I just wanted to let you know that we are going to be offering a free beginning Milky Way photography class later this summer on Tuesday, August 29th. And you're welcome to come to that event, which is at the Pittsfield branch at 6:30 that night. Jason Gunzel, who will be your presenter tonight, is a self-taught astrophotographer from right here in Southeast Michigan. His background is in science and engineering, but he brings a passion for the art of image processing and revealing aspects of the imagery that would otherwise remain unseen. Jason has a large following on Instagram, and his work has been internationally awarded, published, and exhibited through various outlets, including NASA's coveted APOD, which is the Astronomy Picture of the Day, Astronomy Magazine, Sky and Telescope Magazine, and he just recently found out that he's shortlisted for a very competitive astrophotography award. And I think he's the only candidate who took the photo that is part of the shortlist right here on US soil. And Jason does all of this here in Southeast Michigan, which is full of light pollution and is a state notorious for its cloudy lake effect weather. So here to talk about his process and how he confronts all of these obstacles and still manages to get amazing photographs, please welcome Jason Gunzel.
All right, good evening. How about that weather? Okay. Thanks, Amy, and thanks for having me. I'm pleased to see the turnout. We're going to talk about the universe and space. I think that's something everybody has a passing interest in, but I kind of took it to the next level. Let me get my presentation loaded up here on my end. So yeah, as Amy mentioned, I'm a astrophotographer, and what does that mean? Well, I take pictures of space, and it's a hobby of mine. It's become a passion of mine. I've built it kind of over the span of several years, and I hope you enjoy looking at the pictures. For anyone with a short attention span, guilty. I've got a picture on every page, so there's always something to look at. This can be a pretty daunting topic and complicated one, so I hope you don't have any questions with what I'm presenting, but I will have time near the end to go back and reflect on some of the slides if there's questions or spend a little bit more time. So without further ado, I'll just hop forward. As was mentioned, these pictures are all taken by me, the vast majority of them locally. And for me, getting into this initially, I didn't think any of this was possible. So I'm hoping to give you some appreciation for that, and maybe some budding curiosity to maybe get started and enjoy some of this yourself. And the world is changing. We've got social media banging at everybody's door, and the way that this imagery is consumed has been evolving from still pictures to short form video, TikTok and YouTube shorts, all that stuff. So I've kind of evolved with that and tried to present my work in unique and different ways. And so, just as a lead in, this is one example of that, of taking, 2D imagery and making it 3D, giving you a sense of actually flying into these objects or being there. So it's just eye candy, but I find it to be an interesting way to observe and to enjoy the universe. So like I said, let's let this finish up here. This is, by the way, the Cat's Eye Nebula, which is made famous in a Hubble photo. But amateur astrophotography gives you the opportunity to kind of expand the field of view and explore around that. So what is astrophotography? I mean, really, it's just taking pictures of anything that's away from the Earth. Space, the universe, the cosmos. How is it done? And it's really just specialized techniques and equipment. So we use these tools to enable a view that otherwise the human vision wouldn't enable us to see. And so we're focusing on small objects, faint objects, and things that the human eye just can't perceive. And through this new technology, cameras and telescopes have been around for a while, but some of the camera technology is just ever evolving. And they're getting so extraordinarily capable that images that we can take from our backyard now, professional observatories and Hubble Space Telescope was just displaying even just a couple decades ago. So why do I do it, or why did I get into it? I'm a curious person, and to me, it's a sense of exploration. It's going out there and seeing things visible to me that I never knew were there. Anytime I take a picture, anytime I look at or study an image I've taken, I see new things. I see a speck of light, and I'm like, hey, what's that? You know, and there's resources to dive in as deep as you want to explore. And I mean, you can't beat the view. Looking at a galaxy like that on your back patio, that's a pretty amazing thing. So the interest, and this just goes into a little bit about me and my journey. How did I get into this? I've had a curiosity about space in the universe since I was a child. And my parents fostered that. We took trips to Kennedy Space Center or science museums, and I got to kind of get a little sense of what that's all about. But about the age of 10, I received a telescope as a gift for Christmas, and it's just a cheap department store telescope. But what was amazing to me is it opened up this world that was otherwise invisible. I could view planets and the moon, and I still have this telescope, and the video that's playing in the background last summer, I set the thing up again, put the iPhone to the eyepiece, and you can see the live view of the moon there. I mean, it's not terrible for a telescope you could probably find just someone giving away. But again, you can kind of get out what you put into this hobby. You can do it really cheaply. You can do it on a budget, or you can dive in, and spend tons of money and get better results. But I just want the audience to realize that things you may have on your shelf, like a digital SLR camera, enable this. And you can, maybe you're not looking at pictures of galaxy, but maybe you're taking pictures of the sky, nightscapes, like the picture I have on the screen here, which is the moon and Venus setting. This was one of the first, if not the first, astrophoto I ever took, and I got this digital SLR camera in 2009. Just a basic consumer camera, but I immediately just, what can I take pictures of? And I pointed it at the sky, and this slide here, I think, tells a really good story. So I look back on this, and it's somewhat comical to me that the picture on the left was the first picture of a galaxy I ever took. I was astounded at the results. I had the camera I showed on the last slide, the Canon T1i, a cheap lens on the thing. I put it on a tripod. I pointed it at the sky. I knew roughly where the Andromeda galaxy was from sky charts. I snapped a few pictures, and that's the result. And it doesn't look like much, but I lined it up against professional images, and I'm like, wow, that star matches up. That's the main galaxy. I see satellite galaxies. I'm like, I can do this. So just a few years later, I dove in, bought a telescope, and the picture on the right, shot with the exact same camera, by the way, through a pretty basic telescope, a 400 millimeter focal length, 6-inch Newtonian telescope. You can pick one of those up for a couple $100 brand new. And it rides on an equatorial mount, which tracks the sky and enables longer exposures. So you can see here at the bottom that I used 1.5 hours, hour and a half of total exposure time, divided up into individual pictures, and you can assemble those all together and yield a pretty spectacular image of a galaxy. Take that one step further, and using a long focal length telescope, we can zoom in on that. And that little box there in the lower right corner shows the area of the image we're looking at. Within this image of the Andromeda galaxy, we're resolving individual blue supergiant stars in a separate galaxy that's 2.5 million light years away from us. I mean, it's just astounding to me, and I hope it would impress you too that we can see that far across that expanse of space and time to a galaxy and be able to see individual stars and structures and nebulae within those galaxies. So a little, just before we move on, a little bit more about me. I've, as I said, had this lifelong interest in space and astronomy. I went to the University of Michigan, got an aerospace engineering degree, worked in engineering fields, various industries, aerospace, automotive, HVAC, mostly in product design and development and analysis. And really that engineering career prepared me for the problem solving necessary for astrophotography, because there is a lot of it. A lot of times you're winging it out there, you're making mistakes, and you learn from those mistakes, and it's just incremental improvement from there. These days, I do astrophotography as a hobby. I love to share it on social media, other outlets as a form of public outreach, and I think that's what this is here today, to kind of look at some pictures of space and maybe give you a budding interest and maybe wanting to get started. Along the way, I developed my skills to the point where I started getting recognition. NASA Astronomy Picture of the Day, as Amy mentioned. Astronomy Photographer of the Year is a competition running out of Greenwich, England. I had my astrophotography hanging on the wall of a national museum in England because of that. Built quite a following on social media and had the opportunity to author several articles in magazines. I had pictures published and both in physical print and online news outlets and things like that. So let's talk about astrophotography now at a glance. As I said, every slide's going to have a little background image of this is one of my shots that I took from my backyard. And we'll try, I might have missed a few, but I'll try to label it here at the top so you can get an idea of what you're looking at. But this is a galaxy cluster. We're looking at galaxies here that are in the range of millions to billions of light years away. And to get a shot like this, you need to take an incredibly long exposure photograph to collect that light, which is incredibly faint from these distant objects. You have to excuse me, the weather got me a little choked up. I got to drink some water here, but I'll break down now astrophotography into two main paths. And I do this because there's a subset of people that enjoy the science of it, right? There is a component of amateur science going on that feeds into professional science, and that is a viable field that a lot of people go into, and that's observing events out there, taking pictures of them, and submitting those data sets to professional astronomers, and those in turn get published and perhaps credited to the amateur scientists. So it's a really interesting way to go if you're into it. I told you before I like the pretty pictures, and that's kind of the column I inhabit. And there's a lot of things we can look at up there, and I broke them down into several main categories. But the three pillars, I would say, are deep sky, which is galaxies and nebulae; planetary, which is looking at planets within our solar system and the sun and the moon; and nightscapes, which takes an earthly foreground and puts it against the night sky. Extra bits, special events, I call them, are things that happen, or celestial events like eclipses or transits and alignments and aurora. Those are all things that could be lumped under astrophotography and can be considered another subset. All right, so Let's take a look at each one of these: deep sky, planetary, and nightscape. I'm going to break them down and do them individually because they are quite different. And there's a lot of different techniques that can be applied and go into processing these photos. So first we'll start with deep sky. In the background is a photo of an emission nebulae. That's the Elephant Trunk Nebula, which is just a collection of hydrogen and oxygen gases and sulfur up there in the cosmos, condensing into newly born stars. So it's a stellar nursery of some sort. So deep sky astrophotography really deals with capturing distant and faint objects. And I stress the word faint because this is not stuff the human eye can see. If you look up in the night sky, you can really only see one deep sky object, maybe two or three if you're in exceptionally dark skies, but the main one you can see is the Milky Way, which is our own galaxy. So deep sky astrophotography, you really have to focus on faint objects. And to do that, there's a few things that are required. Number one is long exposures. And number two is tracking the sky so that your long exposures aren't blurred. So in this video that's playing, you see my telescopes in a night of observing where I've got three telescopes running. One's set up to capture the Milky Way, and you can see me there on the right adjusting the camera. The other two are pretty much automated, tracking objects in the sky and just taking exposure after exposure. After I get all those exposures, I collect them together and post-processing them, which involves manipulating the image data to produce a picture. Like I said, that's necessary because these things aren't visible to the naked eye. If they were, you'd look up and you'd see all these objects because they are big enough to see with the naked eye, but just too faint. There's really three pieces of equipment, main pieces of equipment that go into it. And this is a picture of some telescopes. I guess I like to operate in pairs of, or sets of three, because I have three telescopes in a lot of these setups, but these are all configured for deep sky imaging, and it gives you kind of an idea of what different systems can look like. The one in the foreground there is a refracting type of telescope. The one in the middle is a SCT, which is a Schmidt-Cassegrain. It's both a refractor and a reflector, and the one behind that is it's called a RASA, but it's a different kind of design where there's a mirror at the back and the camera on the front. Now you can see the cameras here. They're at the back of the two right-hand telescopes, but at the front of the left-hand telescope. And these are those little red cylindrical pieces. These are astronomy cameras dedicated to the task. They are cooled, which means that the camera sensor is reduced in temperature to limit the noise contribution, the thermal noise. And all these telescopes and cameras ride on tracking mounts, and that's what you see below the telescopes themselves. These are equipped to find an object in the sky and track it for as long as possible, and that keeps our exposures consistent. It prevents trailing or blurring of the image as it moves across the sky. And as I mentioned at the bottom, accessories and more accessories. If you ever happen to get into astrophotography, you'll have bins and boxes of things you've acquired and hardly ever use, but it just requires so much ancillary equipment to get all this running consistently. And so it's, I'd be remiss to not mention that as a major factor in getting these up and running. Because consistency is key, and really you need to have reliable results to produce this imagery. So in that vein, I automate as much as possible. I'll have a motorized focuser that the computer controls, telescope pointing the computer controls, tracking. The tracking across the sky is constantly corrected by an auto guider, which is a secondary camera you install on here. And then the computer also can assist in exposure sequencing, which is just telling it what you want it to do, hit go, and the thing will automate itself throughout the night. And it really enables a lot of this, because if I had to sit up and stay up all night every night, telling it to take pictures and telling it what to do, I would never get any sleep. So this, the key enabler here is really sleep on my behalf, because I can get some rest and let these things do their job. So on to post-processing. Post-processing is image editing, and I get this question a lot. Why is it needed? If you're taking an image that you collect and you're editing it, is it real anymore? Well, simple fact is that astrophotography has to be edited. And why does it have to be edited? Because if it wasn't, you wouldn't be able to see anything. You would get the same view your eyes do. So there's a lot of work behind the scenes in assembling the photos, stacking them, which is averaging a huge set of images together, and processing them, which is brightening and adjusting contrast and colors to get it to either a realistic representation of what this object looks like, or there's ways to push it a little bit beyond that. False color imaging is one that comes to mind, where you're not necessarily making up anything, but you're using the information you collected in creative ways to generate a photograph. But through all this, photography rules still apply. If you want to have attractive images, if you want your photography to stand out above the rest, classic photography techniques like composition, exposure control, filtration of light, and composition, they all apply. So you want to try to make a pretty picture, you gotta make it pretty. So again, that's the artistic element to all this. It's not only science. I view it as an art as much as a science. So I talked a little bit about what we see straight out of the camera and why we process data. So on the left here is a single 4-minute raw exposure. Pretty picture? I don't know. I don't think so, but that's what the camera sees. I titled this 65,536 Shades of Gray because that's what the camera registers, okay? It's registering shades of gray. Although this 4-minute exposure doesn't show anything to the human eye, that single shade of gray, which is single shade of gray to our eye, which is just a dark gray, contains a tremendous amount of information. So how do we get that information out of there? Well, we do what's called stretching, which is we take that narrow band of gray, which the camera has captured all these different shades in, and we stretch it out. We make the blacks blacker and we make the whites whiter. And when we do that, we get the middle image. And that's a single 4-minute exposure. It's the same photograph you see on the left, but it's stretched. So we've taken that brightness up and we've taken the contrast up, and we reveal what's hidden in that photo. And one step further, by collecting a multitude of exposures, in this case, 119, which was somewhat arbitrary. It's all I had time for. But you can see what then shows up. We take those shades of gray, and each time we stack another photo on, we get more and more shades of gray, so we can stretch them further and we can reveal what's hidden in the information down there. And so you get all this faint detail, the stranding, and all the granulation within the nebula itself. You may be wondering why it's black and white. Astronomy cameras often are. They don't have to be, but you get some advantages shooting in black and white. And so for astronomy imaging, oftentimes we'll shoot through a clear filter, which is just registering shades of gray. And then we'll come back and shoot through individual red, green, and blue filters to get a true color image, or other filters to get a false color image. So there's a lot of options here in the way that you want to present it. And so I've made this little video so you can kind of see, using that same example on the last slide, of how we get to an image. So I'll let this play a couple times because I'll talk over it. But on the right there, you see me capturing photos. You can see the clock at the bottom going by fast because I'm collecting all this data. I showed the individual photo stretched and now stacked, and then we'll add a color layer on top of that will increase the contrast so that more of that shows up. So we get to a finished photo here, which will reveal all that hidden nebulosity. And here I digitally even removed the stars so you can see even more that information. So what you're looking at here now is a true color representation of that nebula in the sky that I spent hours and hours collecting data on. I took hundreds of individual photos. I stacked them together. I took color information and I've integrated that all together to make that single photo. So once we get all these sub-exposures, we pre-process them, which is calibrating them to remove defects, weighting them, aligning them, stacking them, making initial adjustments, combining all these master frames we get, and final image adjustments. All this goes into making a single photo. And I hope you can appreciate that taking the pictures is only half the battle. The assembling and the processing and everything that happens after that is a whole nother endeavor. And a lot of it's time, it's all sitting behind a computer. There's software that will automate and complete these tasks. So it's not worth being overwhelmed about all of it, but it is a lot of steps and it's a lot of things going on behind the scenes. So I hope that gives some appreciation as far as what you see in an astrophoto. All right, so deep sky astrophotography, like I said, I do a lot of it for my backyard, but there's severe disadvantages to doing it from a populated area. And you can see in this chart here, this is a light pollution map. So it shows the light pollution scale on a scale of black to white being the worst. You can see cities show up as white. As you get outside those cities, the light pollution fades. But around here, you've got to get north to even be in an area of low light pollution. And have to go all the way to the Upper Peninsula where it's considered negligible. So this is an issue that we always deal with as astrophotographers. There are ways to get around it, and I'll show that a little bit here. One thing I already mentioned was to shoot long total integration times, hundreds, thousands of pictures. By doing that, you're taking that light pollution, which is somewhat random, and you're averaging it down. So that's an effect that you can then subtract, but you have to be real careful shooting. I've got this video playing of a night at my house. I mean, it's somewhat clear at times, but it's not worth shooting in because you've got a major light pollution component. You can see the glow on the horizon and you've got these thin clouds passing through. The telescope would happily shoot through this, but the results would be terrible. So, a couple tricks that we kind of abide by are to shoot on moonless nights, shoot when things are high up in the sky, and avoid any session like I'm showing here on the right. And try to get yourself to dark skies, but out of convenience, most people that shoot a lot will shoot from their house. All right, so that wraps up deep sky. We'll hop on to planetary now. It's a whole different ballgame, and you're still taking pictures of space and deep sky objects, but you're doing it in a completely different way. And why is that? Well, these things are bright. In contrast to deep sky objects, you can see them with your naked eye. The trick to them is that they're extraordinarily tiny, or if they're not, like the moon or the sun, you're trying to resolve very tiny details on them. So you've got a different set of challenges, and so the process is a little bit different. And I will say here that some people that get into astrophotography, they'll go down one avenue or the other. I happen to kind of dabble in everything, but there's some people that just specialize in, say, planetary astrophotography, and that's what they do. There are, as I said, different challenges because we're looking at these tiny details. The views are highly magnified, so the quality of your optical system, the telescope, and how you align it and use it are very important. Not only that, but weather plays a huge role The view through the telescope itself, or the live view that you get on your computer monitor, is great because you can see the objects real time. You can see them dancing around. A lot of objects like the moon and the sun, they're, well, even some of the planets, they're ever changing because planets rotate fast. Jupiter, in the time that you observe it, you can actually see it rotating. The sun is incredibly dynamic. The moon, every time you come back, the shadows are different. So it's always interesting. And again, because of the way we have to do this, because of the handicaps we have shooting through the atmosphere, we have to process these images to get clarity back and to reveal details that are otherwise lost. Fairly similar to deep sky, though, the key pieces are telescopes, cameras, and mounts. You don't need the same types. And as a matter of fact, for planetary astrophotography, large telescopes excel, and that's because of some properties of optical physics. You can get higher resolution if you use a larger telescope, and it enables you to also get a longer focal length, zoom in a little bit more. And like I said in the previous section, accessories, it's just a constant battle with trying to get the gear you need and have it working right. Planetary astrophotography, as I mentioned, it's the details. This is one of my best shots at Jupiter, but it's a long time coming, and it's extremely tough to get a detailed shot, especially from our location. But you're trying to extract the tiniest details you can on a telescope that's shooting at a focal length of 6,000, 7,000 millimeters. Might be nonsensical if you've never done it, but the precision required and the attention to detail is kind of off the charts. So you have a lot of sessions, you go out, you shoot, and the results are just not even worth a second look. But sometimes everything, the planets align, as they say, and you get just astounding results. So like I said, the large aperture telescopes help. Focus is always an issue with trying to dial that in precisely, and collimating or optical alignment of your telescope is important, and that's something that you can control. It's hard to get it exactly right. And then the wild card here is astronomic or atmospheric seeing, and that's the blurring introduced by the atmosphere. And that's because when we shoot through a large air column, just like heat plumes over a highway, it's constantly moving. And what you're seeing is turbulence in the air column, both upper atmosphere, and it could be right in front of your telescope. A cement pad could be sending off a heat plume, and that simple issue can create problems in your optical train. So that effect that I'm talking about is what you see here in this live view of Saturn. This is the capture software I use, called Fire Capture, but this is what you see through the telescope. That wobbling and the jittering, those are the effects of atmospheric seeing. So that's what we're trying to combat. Now, you can imagine there's some challenges to collecting photos this way. We try to minimize the exposure time, completely contrary to deep sky astrophotography, where we're taking long exposures. We're taking millisecond exposures here to try to freeze that wobbling and that jiggling effect to try to get a crisp photo. And we capture as many frames as possible, thousands, tens of thousands, so we can reject out anything that's subpar or blurry, keeping only the good stuff and then stacking that up into a master frame. So here I show that process where we've collected thousands of images and we stack those together, which essentially means we average them together. Well, you imagine if you average together thousands of images jiggling like that, you end up with a blurry master frame. So that's the raw stack you see here. It's got some clarity to it, but as you can tell, there's some blurring that's happening here. Fortunate for us and modern technology, some mathematicians were on it, and they figured out how to extract sharp detail from blurry images. And that we use a lot of those tools that came out of optical sciences and image processing, and we can take that raw stack, apply these sharpening routines, and come into the middle image where we've made details crisp that were otherwise not visible in the initial image. And the Cassini divide and Saturn's rings, or the bands of atmosphere, those things all pop into visibility once you sharpen them. Planetary processing is fun because you can hit that button. Once you get the raw stack and you're working on sharpening, these views just kind of snap into visibility, and it's like putting on a set of glasses, really. I do planetary similar to the way I do deep sky, where I'm shooting in monochrome. So I'm shooting color information separately and then layering that in. So the images you end up with are true color representations, but it was all captured separately. So like I said, it's a lesson in patience and very exacting shooting planetary. You've got to kind of dial in your system. So you wait for good conditions, good weather conditions. The challenge here in Michigan is it's always challenging in Michigan for deep sky. It's the light pollution, but here it's seeing, so it's the turbulence in the atmosphere. There are predictive tools though, and astronomy weather apps that predict seeing, so they color code it. So you can kind of set up and go out on good nights, nights that it's going to be favorable for doing this type of imaging. And it is the biggest challenge. So you'll see excellent planetary astrophotography come out of locations with dense, thick air, humid conditions like Texas, or a lot of times areas adjacent to bodies of water will get good seeing. Probably bigger than like Lake Michigan, but tropical islands or islands in the middle of the ocean, they'll get phenomenal stability in the atmosphere. And that's just because that air moves unimpeded over the ocean for miles and miles and miles, and it doesn't have obstructions like mountains or trees or buildings. And so those are really where you see some of the best stuff come out of. But doesn't mean that it can't happen here in Michigan. And we'll get some good nights, and you just got to be prepared and take advantage. Kind of the adjunct to planetary photography or the lunar and solar work. Similar in process, but I just have to put the caveat that if you're doing solar observing, you really need to have a dedicated telescope that's equipped for the task. Very dangerous to point a telescope like this at the sun if you're not prepared for it. But I do a lot of solar photography. I really enjoy it. I've got a dedicated setup you see here in the middle, and that shot on the right is a close-up of the solar surface. And what you're seeing there are strands of hydrogen plasma standing up above the surface of the sun. You see a sunspot there, and the bright spots are components of an active region on the solar surface. My plan was to bring a solar telescope here today so we could do some live observing, but the weather didn't cooperate. But maybe sometime in the future. All right, so the last kind of category of astrophotography that I'm going to talk about here is nightscape photography. And this is a fun one because you have opportunity to be pretty creative with framing and composition, because you're putting a foreground object in there, contrary to shooting the night sky where you don't have a foreground. You don't have a lot of choices with where you place things in the image. So I enjoy getting out and doing this. The thing for me is it involves a bit of travel, so it is a little involved in that regard, but I would say it's probably the easiest entry into the hobby because you can get started with pretty basic equipment. If you have access to any kind of camera you can control the exposure on, you can do it. People do it with smartphones too, so you may be carrying around in your pocket an enabling tool for astrophotography. One trick that I like to employ here is still to use a tracking mount, and that enables me to take long exposures of the sky so you can get some detailed images of the sky to put against the foreground. So on the right-hand side here is my nightscape rig, I call it, which is just a simple travel tripod, a tracking unit, which is a basic star tracker that's called a Skywatcher Star Adventure. And then I'll put my DSLR on top of that and go out and take pictures. So here's one such image. This was taken from the summit of Haleakala in Hawaii, looking towards the Big Island. I took the picture in the morning twilight, so you see kind of the dawn colors rising up, and you also see the band of the Milky Way from a phenomenal shooting location, which is very low light pollution, high altitude, so it allows you to see aspects of the Milky Way that I cannot see from home, and they're high in the sky also. But I have the goal of kind of using the natural light of the scene, so I still take long exposures of both the sky and the ground, and I blend those together in post-processing. So this is a little kind of pictorial on how I do that. This was taken in the Upper Peninsula of Michigan. I'll take a set of exposures for the sky, which is on a tracker, so I'm tracking with the sky, so the stars are pinpoint and not trailed. Then I turn that tracker off, and I'll take a set of exposures for the ground, where the ground is in crisp detail. In post-processing, I'll assemble those together and basically blend one into the other along the horizon line. And so it's technically a composite photo at that point, because you're taking two different photos and blending them together. But I have no issue doing that just to get a crisp photo of the entire scene. Obviously, this is all taken on site without moving the tripod. So it's a, pretty good representation of that scene, and rather beautiful. When you get the long exposure dialed in, you can accentuate the coloration in the scene. You get the star colors, the colors in the Milky Way, the reds of the nebulae, the horizon line, which was just around the setting moon. So you get kind of that glow of the moon set. And I think that's actually Traverse City on the left-hand side that you see the light glow emanating from the horizon. All right, so that's nightscape. So I don't know how many people in this crowd are actually interested in astrophotography to the point of trying to dive in. Maybe you're just here to see pictures of space. I don't know, but I'm going to talk a little bit about considerations on how you can get started and what kind of person I see typically get into this. So I call it the discipline of amateur astrophotography, and I underline discipline because I think it's an exacting endeavor. You have to be a little bit detail oriented. Not only have to have those traits of, I'm curious about it, I want to learn about it, I'm inquisitive, but you have to be patient, and you have to want it bad. So the persistence and dedication come in. But also you're set up initially, at least, to fail a lot. So you have to be adaptive, and you have to be okay with making mistakes, getting poor results, or not getting what you wanted. And don't be discouraged by that. Take that as a learning experience.
Attention, please. The library will close in 15 minutes. The internet stations will automatically shut off at 7:55. Please make any final copies at this time and take all materials to be checked out to a self-check station or to the circulation desk by 7:55. Thank you.
So not to get discouraged, you will fail. I mean, I've got hard drives full of just images I don't want to show anybody, but you make the mistakes, you move on, you learn the mistakes you made, and you have to be willing to recognize the problem and learn how to correct it. So that's the problem solving part of it. There's tons of resources out there, and they're getting more numerous by the day. You can start with what you have. Like I said, a smartphone is adequate to at least take some pictures of the Milky Way or get out there in dark skies and take a series of pictures and learn how to manipulate those. Take a set of them and learn how to stack them. If you don't know how to do it, that's okay. Nobody does starting out, but there's a lot of resources, like I said. When I started doing it, it was hard to find someone to talk about with that. I ended up finding an online forum, which I really kind of connected with, and that's called Cloudy Nights. But there's several online forums. But now there's social media, which shows you what's possible. That just wasn't around a decade ago when I started, at least not to the level it is now. But there's classic ones like astronomy clubs where you can find a personal mentor. There's physical books, like I said, online forum, online resources, YouTube. Know how you like to learn and go after that. Because if you look for it, you'll find it. Yeah, so it's all about finding a learning preference. And once you have that resource, can learn what you're doing wrong or how to advance your capability, the sky's the limit, and pun is intended. So next steps, I mean, for me or anybody, it's science and it's art. So have fun with it. You know, if there are things you want to learn about the universe or the cosmos, this is a great gateway to that. You can take a photo and you can explore it to your heart's content. You'll find things that you didn't even know existed. And the technology is advancing so fast. The capability of these camera systems and telescopes are evolving. You don't have to know the fundamentals. It's very helpful to know the fundamentals, but you can go out there, you can buy a telescope that automates everything. You can get these pictures, download to your phone, and done. And take it from there with whatever you want. If you want to share it, if you want to explore it, you can go down those paths. But also, it's an art, and this is what I really enjoy about it. Is it's an opportunity for me to take my science background and be creative with it. I love presenting these things and in ways, unique ways that other people don't, in ways that they haven't been seen before. Shoot them in a unique way, present them in a unique way. And so again, you know, the sky's the limit with that. But at least for me in this hobby, I'm not going to stop learning or innovating or trying to do things differently, because that's what's fun about it for me. So, you know, I hope that enthusiasm kind of comes through in the presentation. I just enjoy it. I enjoy it immensely. And I'll open it up now to questions. Before I do that, I'll say that if you want to see more of my work, I've got a multitude of slides that we can go through after this that show, you know, each branch of astrophotography as I described it, and photos that I've shot, and a little bit about each one. So we can look at that stuff if you're curious. Also, if you want to know more about me and you don't have time to stay or you don't want to stay, you can find my website. I labeled myself The Vast Reaches, so I've got a website entitled that, and I also have the username The Vast Reaches on all social media outlets, so you can go look at my work there. Pretty much all the major ones I use or display work on, and sometimes it can be an engaging community, and I get lots of comments and answer those questions and go through a little bit of my process and things like that. So yeah, by all means, if you're curious, you want to see that work, you have questions for me, reach out to me on one of these channels and we can connect. But at this point, I'd just like to see if there's any questions in the crowd, and I'll go through the remainder of my slides if not. So
I have a microphone here.
Hi, so I have
Hi.
two questions.
Yeah.
The first question is, so you have millions of pictures. How do you store these pictures and document them?
yeah, it's a problem. It really is, and not so much for the deep sky work, because though you can take hundreds or thousands of pictures of an object, that pales in comparison to shooting planetary, where, I mean, literally in one session of solar imaging, I'll have taken hundreds of thousands, if not million frames, and those all have to be stored. So I usually capture them to an external hard drive, which is fast, like a solid state drive. But then I offload them to, I've got network attached storage at my house with, I don't know, right now it's at like 56 terabytes of storage, which is getting close to filled. You can acquire a tremendous amount of data, and it's almost hilarious that you can, in one session, collect a terabyte of data and distill that down to one JPEG photograph that's, 100 kilobytes or something like that. But, it takes all that information to kind of distill it down. So yeah, storage is a problem. I'd buy 8 terabyte hard drives from Costco like they were candy for a while. And then I built this NAS that I can, locally store everything. I'm a digital pack rat, and I admit that, but at the same time, a lot of effort goes into collecting this, and I can't stand to press the delete button. I don't know. But once you process the images, there's a lot you can get rid of. So you don't have to be like me, but I think a lot of people that end up going down the same path as I have, you've got a storage problem. Do you have another question?
Yeah, so my other question is, with your competitions, what do they typically look for to constitute, a good image and, whatnot?
You're talking about like photography competitions?
Yeah.
Yeah, I mean, an astrophotography one is not much different than a normal or like a nature photography one. They do and a lot of times the panels of judges are not dedicated astrophotographers, so they're looking at typical photographic things like composition and framing and exposure balance and balancing negative and those kind of things. I think in at least photo competitions, those are properties they look for. But by all means, you need to have a technically sound image too. That you can't have oblong stars or blown out highlights or things like that. So that's pretty typical.
So you didn't talk about celestial event astrophotography, and I'm just wondering, is that because it's just not your bag, or is it because it's harder to sort of get into because of the
I think
rareness of it or the technical details of doing it?
Well, there's a lot that fit under that umbrella, to be honest. But I do have some slides at the end. We can go through that. I don't consider it one of the pillars because, in a way, most of those events kind of fit under one of the other categories, like they're in that style. So yes, I do view it as a separate category, but a lot of times, like if you're taking pictures of aurora or something, I think that kind of fits with nightscape, and you can use the same techniques. And so that's why I didn't have a dedicated category. Hope that answers the question.
So when you're taking exposures, how many color filter pictures do you take versus your just like black and white main stack?
Yeah, there's a few different ways to do this, and it differs maybe by the style. If you take pictures of nebulae,
Your attention, please. The library will close in 5 minutes. If you have materials to check out, please go to the self-check station or to the circulation desk now.
and
Thank you.
just so this group knows, I think we have approval to go a little bit beyond
Yeah, just a
closing
little,
time. So
yeah.
don't be scared by the announcements. But yeah, so there's a few different styles. If you're taking like a true color image, where you're shooting through a luminance, which is a clear filter, and then you're taking individual red, green, and blue exposures, there's kind of a bogey I shoot for where I try to do maybe 6 luminance exposures to 1 each of RGB. That's not any hard rule. And that's kind of a rule to be broken. I think generally I shoot for maximizing my luminance exposures because that is where the visual detail comes from. And that's where the foundation of the image comes from. The color information maybe is added on top after, so it can be maybe subpar a little bit compared to the luminance. So you would not take as many of those. But yeah, I'll set it up to do like that 6:1 ratio, but once I hit a certain threshold with RGB frames, I'll kind of stop doing that and maybe keep going with the luminance. Not a hard rule. So hopefully that answers that.
Yeah, so it sounds like stacking images is really what unlocks sort of the next level for this. If you've tried night photography, haven't done that.
Yeah.
If you're going to do any sort of stacking, is tracking hardware essential, or can you get started stacking with just a couple of
No,
images? And
it's
get some
really
result?
not. It's really not. So the tracking is to keep your stars around or pinpoint, right? Because the sky is moving. Well, we're moving, but you know what I mean? Like in order to get a telescope trained on a spot in the sky, it has to be rotating exactly opposite of the Earth's rotation to get that pinpoint stars. But that effect is more apparent at longer focal length. So if you're shooting at 600 millimeter focal length, or, really zoomed in, those stars are going to trail in the span of half a second. But if you're shooting a wide angle view of the night sky, like a 14 millimeter camera lens, or even, up to about 15 millimeter camera lens, you can get away with shooting a longer exposure without tracking, and you won't see the apparent trailing. So in that way, if you keep your exposure short, you can do the stacking. And that's actually a good way to combat the noise problem, is to stack images. So if you want to take and I used to do this before I did the tracked sky and nightscape, I would do, shorter 20-second or 15-second sky exposures, and I'd do 10 of them or something, and you stack them together and you could reduce noise that way. You can even do it with deep sky shots. If you take like a 1-second exposure, it just looks like a black screen, but you can actually stack those and extract detail that way. So yeah, lots possible in that regard. And it's getting more possible every year as the camera sensors are getting better and better and able to resolve details at lower and lower exposure levels. You can imagine that you can get away with quite a bit that you couldn't in years past. So yes, you can stack absolutely without having to track.
Any other questions?
All right, well, if there's no questions, then feel free at any point to raise your hand and ask. It's the end of my planned presentation, but I've got all these slides we can look at, just pretty pictures of space. I'll go through those, and feel free to raise your hand if you have questions. So if you want to see anything in particular, we can dive a little bit deeper. I've got these broken down by category also in the same order as we looked at in the presentation. So we'll do deep skies first. And these, again, they're just going to be pictures of the universe captured from my backyard using different filters. Here, a little bit different than the main presentation, I've got some information on what was used to capture that photograph and a little bit about the object itself. So this is...
Attention, please. The library is now closed.
You're not locked in, I don't think. You have to look at everything I have. So this is a end-of-life star up in the Milky Way that it's basically shedding layers of its atmosphere in an interesting way, because the red tones are hydrogen and the blue tones are oxygen. These are ionized from within. That central star is actually causing this nebula to glow. So when we're taking pictures of it, it's actually physically glowing there in outer space. And this is called a Wolf-Rayet star. It's a rare type of star, but again, shedding its atmosphere, and so we get to view these layers of atmosphere. There are several examples up there accessible to us, but this is one of the most well-known. It's known as the Crescent Nebula. You can see I shot this through narrowband filters, which hone in on a very specific wavelength of light. So we can see that ionized hydrogen and the ionized oxygen. And then it was shot also through RGB filters to give the stars true color. And this is essentially a true color image built up out of all these individual filters, totaling 26.7 hours of total exposure. This one, as I say, needs very little introduction. This is the Pillars of Creation, which Hubble made famous in its classic photo of this area. Star-forming region, pocket of hydrogen gas carved out by these newborn stars and condensing and gravitationally pulling on these columns, and also the energy from these newborn stars are pushing on the clouds of gas. So you get this just sculpted nebula that we see here from across the expanse of 7,000 light years. So again, this is within the Milky Way, and it's a pretty local star-forming region. This is a planetary nebula. So this is again an end-of-life star, shown in true color again, but shot through narrowband filters. So it's just expanding gases of outer atmospheric layers of the star as it's in its death throes, and in red giant phase, it's kind of blowing off these layers of atmosphere, and these are energized and glow from the radiation within. I love this shot of this planetary nebula because I was able to pull an exceptional amount of detail out of the core there. You can see my image there on the left down below against the Hubble Space Telescope rendition there. So obviously I didn't match that level of detail, but looking back and forth, the structures are there. So it's a pretty exciting result. This is known as an irregular galaxy. This is the Cocoon Galaxy. And you see a pair of galaxies that have actually collided, and the magenta tones here, the strands and the blobs of magenta, those are ionized hydrogen, indicating areas of starbirth. So because these galaxies kind of passed through each other and collided, it sparked a whole new round of stellar formation. And that's what we see with that kind of cage of hydrogen wrapped around the main galaxy there. This is the Wizard Nebula, which is a collection of hydrogen and oxygen gas, another stellar nursery within the Milky Way. IC 342, which is a face-on spiral galaxy, just a beautiful galaxy. Interesting one because we see this beautiful galaxy through the veil of Milky Way dust. So it's a distant galaxy. I think it's something 20 to 40 million light years from us, but we look at it through the Milky Way. So between us and this galaxy is a layer of dust within the Milky Way. And so it gives the galaxy itself this ruddy cast, and you can see that haze kind of within the stars in the foreground there. I really love the way this one came out too, because you get the kind of smoky appearance, fitting for the day, right? This one is called the Dark Shark, which is another nebula within the Milky Way. What we see here is columns of dust, essentially, and these are all components of starbirth, but some areas, these clouds are condensing to form new stars, and we get stranding of magenta, which is again remnants of old supernova. We've got a planetary nebula there, which is glowing in the teals and the magentas. So just kind of like a vista shot with a really wide angle telescope to kind of to get all these structures within a single field of view. This is shot in with a 180 millimeter focal length, so you can imagine that's within the range of a typical camera lens. So really, we're looking at an expansive sky here. I think it's 5 degrees across. You know, real big field of view. This is an interesting one, Messier 76, the Little Dumbbell Nebula. This is a red giant star, which is an end-of-life star, right next to a planetary nebula, which is an end-of-life star. So that star, that big orange star at the top, is going to turn into something like what we see in the lower right, which is a planetary nebula. Looking a little more distant, we see a beautiful edge-on spiral galaxy, which is NGC 891. Edge-on galaxies are interesting because we're looking right along that plane of the galaxy. So we get a pretty similar view to how we see our own Milky Way, where we get the dust laying through the center. And we get these tendrils of gases and nebulae that kind of extend out in either direction, all kind of superimposed on a layer of a diffuse halo of stars behind. This is Messier 1, the Crab Nebula. This is a supernova remnant. This star exploded, and I got it on here, on the 4th of July in 1054. Nice 4th of July firework. Noted by Chinese astronomers at the time, so they've got records of this star being visible in the daylight as this thing exploded. And here we are 1,000 years later, and you can actually year to year see this nebula still expanding. And that's how they originally knew about when it occurred, because you can kind of trace that expansion back into a point. But this is a really interesting target. It's got tons of layers of intricate details. In the blue here, you see what's called the pulsar wind nebula. So it's got a central pulsar and this little disk of gases. Let me see if I can get the mouse over there. There's a little disk of gas swirling around here. Then there's these jets, they're called polar jets, coming out of the poles of the pulsar. And what a pulsar is just a rapidly spinning star that's sending energy out in repeated fashion. So it's got this pulsing signature, which can actually be observed real time. All right, so that's deep space, planetary. These are always fun ones to look at. And again, the planets are always changing. I need to update this slide because we flew by Mars, not in 2020, but again in 2022, but we had terrible weather for it. So this is my best opposition Mars photo, and opposition is just when we're inside Mars orbit. So we fly by Mars once every 2 years and change. And so we get Mars increasing in size to a maximum, and then as we pass it by, it slowly fades again and gets smaller and stays like that for 2 years. So every couple of years, we get a really nice view of it. It gets to be one of the larger apparent planets, and we can get some details. You can see here some of the surface. I will be wrong if I try to call these out by name, but all these surface features, areas of ruddy Martian soil, and then the more mountainous features show up a little darker, and you got the South Polar ice cap there visible also. But again, just to hammer home the point of how many frames I'll shoot on a planetary session, I captured 45,000 images of Mars to get this photo. Here's Jupiter, the king. It's always a fun one to shoot because it's large, and Jupiter will rotate once every 10 hours. So in 5 hours of observation, you can see the entire planet as it revolves. You see one side, and then 5 hours later, you see the exact opposite side of the planet. presents some challenges for astrophotography because as it's rotating, it's actually over the span of your capture, it will blur details. So you need to use special processing techniques on Jupiter to they call it derotation, where you line up all the features of the planet to get a crisp feature. But in that regard, it's always changing. Every year you come back, the cloud patterns are different, the banding is different, the storms are in different locations. You can actually observe Jupiter over the span of weeks and months and see the storms rotating or moving locations. That's really an interesting thing to study photographically. And Venus, which is up in the evening sky right now, available for some nice views. It goes through some really, because it's between us and the sun, goes through some really nice crescent phases. And so you get to see that change night to night. And if you shoot Venus with an extended spectrum, meaning near infrared and ultraviolet, which the cameras will capture, you can see some details in the cloud decks of Venus become apparent. So that lends the color to the image, where you can see areas where the ultraviolet light is scattered differently through the clouds. Observing Saturn over the course of many years allows you to see another effect where Saturn has a polar tilt. So over time, if we come back year after year and take another photo of it, we can see this tilt. So I've assembled all those images together and play them back as a video, so you can kind of see we get a different angle of Saturn each year. And in the coming years, these rings are going to go so far as to tilt edge on, so they'll almost disappear from our view. I haven't yet put last year's photo in this, and it's getting time to put this year's photo in this. So I will soon have 10 years of observation on this. And so I'm planning on keep adding to this and looking at it over time. All right, so on to solar, which I mentioned earlier, although we didn't really talk about it. I love doing solar observation. Again, it's incredibly dynamic target. Using specialized filtration, we can look at the chromosphere of the sun, and the chromosphere are these dark tendrils. And those are columns of hydrogen plasma that are above the photosphere of the sun and kind of blot out the photosphere below. And it's been likened to like a dusty light bulb, where you're seeing this structure on the outside of a very bright sun. But this filter that I use hones in on that specific wavelength, very narrow bandpass, and allows us to pick that structure out. There's different ways to visualize this and look at it. One interesting way here is, this is kind of a natural presentation. You can flip the tonality so that it's inverted, and it allows you to see the hydrogen structures a little more. You'll see one of those in a bit. But I've also got the capability to observe the sun in other wavelengths. This is looking at it in the ultraviolet or close to the ultraviolet. And different structures show up. These are, you can see surface granulation, and the active regions show up as brighter spots, and you got the dark sunspots still. But it allows you to just observe the sun in a different way. And again, just really interesting stuff, because the sun rotates fast too, and over the span of your observation, you'll see the rotation, you'll see things come into view, you'll see the surface undulating and moving. You'll see prominences, which are areas of the chromosphere that extend off the limb or the edge of the sun, and those are incredibly dynamic also. I've creatively found ways to present the sun, where I teamed up with another astrophotographer, and we combined tens of thousands of photos of the sun taken at different times to kind of build this composite view of what the sun would look like if our cameras and our eyes could see it in this way. So we've got multiple layers of atmosphere here. We've got the chromosphere, the photosphere, prominences. We've got the solar corona extending away. So this is one of those that it's a composite photo, so it pushes a bit more into the art side of astrophotography, but we really enjoyed this project because it allowed us to see the sun in a unique way that probably no one's ever viewed it. So I'll show you the sun in motion here, what we can do if we time lapse the surface of the sun. This was over the span of 23 minutes, just a few weeks ago. It shows you just how much movement we see in the solar features over that time span. So it looks somewhat static, zoomed out, but once you look into the details, you can really see that just churning atmosphere of the sun. And occasionally you'll see flares or big burps of hydrogen plasma that shoot off the surface of the sun. It's really kind of fascinating and mesmerizing to watch. Here's another one, just kind of looking at it in a different way. It gives you a visualization of a solar prominence there moving on the edge of the sun. All right, so on to the moon. Fun way to present the moon is to saturate the colors, incredibly saturate the colors. So you're starting to see differences in the regolith of the surface of the moon, the different mineralogy by looking at it in this way. And so the blue tones are titanium-rich areas of the soil of the moon, and then the more rusty colored, well, they're rust colored because it's got a high rust component. So these are a lot of the same minerals we find here on Earth, but they've been exposed to the space weather for so long that we can take these exposures, saturate the colors, and we get what's called a mineral moon. So we can see the interesting details. One area I like to look at are these rays that come out of some of the younger craters. These are called ejecta rays, where the material has just been thrown up and deposited over top of these larger areas. And this is a composite view of the moon where I took many, many photographs of the moon over time and assembled it into this view to kind of represent a little bit how it looks to the eye. But again, it's hard to photograph it in this way, so composite photography is one of the only ways where you can kind of put a photo like this together and see it all in one shot. The moon's tough because it doesn't appear, the same side of the moon always faces us, right? We always see the same thing. But it changes every day. It wobbles and it tilts a little bit. So getting things to line up is a challenge. It can be done in software. Basically, you can map your image to a sphere and get it lined up and stuff. It's a complex way to do it, possible, but I stack images of the sun or of the moon when I make photographs, but they're all shot within minutes of each other, you know. Yeah, wrap it up. Okay. I'll just hop through. I got a few nightscape photos. I love doing this. Unique way to view the world around us. We're talking about special events. This is one such event where you can visualize comets moving against background stars. Here's another comet, Neowise. You might remember it from a few years ago. This is a time lapse of it moving over my house. Never got a good shot of it because of the clouds, but you can see that here. I won't go into this one because it's a little bit of an explanation, but another special event you can capture is the International Space Station crossing the sun. So this is, looks like a TIE fighter, but that's the space station transiting the sun, and you can get predictions for this. You can photograph it. You can photograph it even with a standard camera and solar filter. So Really cool thing to do. Special events, total solar eclipse. Those are awesome. If you've never been, go see one. This was the 2017 one I got a photo of. Just incredible, incredible thing to go see. If you like space or natural events, go see it. This is the blood moon, total lunar eclipse, although this is just as it was passing into Earth's shadow. You get really cool coloration on the moon and can shoot that with some of the lunar techniques to get high detail image of the moon. This is a partial solar eclipse behind the Mackinac Bridge shot in 2021. And aurora, only had one shot to see it overhead. This was from Iceland, but luckily had my camera there to shoot up. I think this is about a half-hour time lapse of the aurora dancing over my head. But like I said, you can do this stuff with just a simple camera. This sequence here was shot with a GoPro. So you get up to dark enough skies, you can do this with something as simple as that. All right. So been asked to wrap it up. Thank you. I hope my enthusiasm comes through. I hope you enjoyed the pictures. And if you want to find me, website, social media, by all means, I participate locally in some live groups. But if you have any questions, feel free to grab me before you leave, but or find me online. All right. I appreciate everybody for coming out. Great turnout. I'm glad everybody stayed because that means that you're interested. So
You got a
thanks.
book? Is there a book?
I don't have a book. I've thought
There will be.
Yeah, there will be.